4.1 in Pre-Calculus Clip 2, Angles of Elevation and Angles of Depression. Well, these are formed with a horizontal line. So I can have somebody standing here and they're looking out, their sight line is a horizontal line. And if they look up from that horizontal line, then this is called an angle of elevation. So from the horizontal line and then up to form it. So it rotates in an upward direction. If the person, however, if I had a person up here and they were looking straight out on a horizontal line, and then they decide to look down to the other person or down to get this direction, that would be an angle of depression. So all of these are defined with looking straight out on a horizontal path. Are you tilting and are you rotating upward to get your angle, or are you rotating downward to get your angle from this location? Now, when people do this, you can see, I'll draw this shape. See, these two triangles are supposed to be the same if I drew it right. If this is a right triangle and this is a right angle, here's a horizontal line. Going from here to here is an angle of depression. It's sad because it's depressed, it's right there. And going from here to here is an angle of elevation because it's going from the horizon up. If you recall from way back in geometry, we've got a horizontal line and a horizontal line here. Those are parallel lines. And so if I trace them, they make this letter Z. Most of you probably won't remember this, but this angle and this angle are alternate interior angles. Therefore, by the alternate interior angle theorem from back in geometry, the angle of depression is congruent to this angle of elevation. So when we're solving problems, I have students who really struggle to draw this triangle. For some reason, they always want the horizontal to be down here. So I say, well, if you like to draw this triangle and you're told it's an angle of depression, turn that frown upside down and put it right there, because they're congruent. So take that angle of depression and turn it into an angle of elevation as you set up your problem. Let's take a look at an application problem. The ground crew worker who is 6 feet tall, that's going to be important because that's where our sight line is. So this is 6 feet from here to here. Is directing a plane on a runway that is 150 feet above the ground. So here's our airplane. Mr. Ritter's not a very good artist, so you'll have to forgive me. There's our airplane, and this airplane, we know its altitude is 100, is that what it says? 150 feet above the ground as it's coming into land. Oh wait, that's 150 feet above the ground. So wait a second, that's this whole thing, which means that this little part of it right here is 150 minus 6. So this is 144 feet. So we have this, they tell us that it's an angle of elevation of 32 degrees. So he was looking straight out, he tilts his eyesight up to see the plane, that's a 32-degree angle of elevation. So we have this triangle, and we are asked to find the horizontal distance from this person to where the plane is currently above the ground. So we're finding this distance. Well, with respect to our 32-degree angle, the 144 feet from the sight line to the top up to the plane is the opposite side, and the horizontal distance is the adjacent. So we're going to use tangent. Tangent of 32 degrees equals 144 feet over x. So I cross multiply, I have 144 equals x times tangent of 32. I do 144 divided by the tangent of 32 degrees, whoops. And I get that x is approximately, it said round to the nearest, it didn't say, so we'll round to the nearest foot. Roughly 230 feet away. Now again, I may give you a problem that has an angle of depression instead. If I said the plane has an angle of depression of 32 degrees, then you would turn that frown upside down and change that into an angle of elevation. You could solve this triangle instead. We'll see some more problems like that in class. Solving a right triangle, you all should know the triangle sum theorem, which says that if you already have two angles, you can find the third angle by subtracting the other two from 180. You should all know Pythagorean's theorem, a squared plus b squared equals c squared. If I give you two angles, you can use the triangle sum theorem. If I give you two sides, you can use Pythagorean's theorem. If you found one of those sides, you really shouldn't, and I'll give you an example of that in a second. Now, the other thing we have to find for sides, if we are given a side and an angle, we can do SOH-CAH-TOA to find sides. And if we are given all sides, or given two sets of sides, we can do the inverse trig ratios to get angles. So you already knew, and honestly you did all this in geometry too, but in middle school you knew the triangle sum theorem, in middle school you knew Pythagorean's theorem. In geometry we added how to solve triangle sides using SOH-CAH-TOA, and we did that in the first clip, and how to find angles using the trig inverse of the ratio to get the angle. We also did that in the first clip of this lesson. So here's an example. We are asked to solve each triangle round to the nearest tenth for angles and, or nearest tenth for side lengths and angles to the nearest degree. So we have to find everything that's missing. Well, I've been given two sides. So I'm going to find this third side by doing Pythagorean's theorem. Be careful, that says c, but it's not the hypotenuse. So c squared plus 20 squared equals 37 squared. 37 squared minus 20 squared is 969. They didn't say simplest radical form, so I can totally just do the can just totally just do the square root. I don't have to break down the 969. It's 31.13 when I round to the nearest, oh, it said nearest tenth. Okay, sorry. 31.1 to the nearest tenth is the length of side AB. Length of side AB is 31.1. All I did was Pythagorean's theorem to find that. As I find my angles, angle B is already given, so I don't have to find the ones that were given, but I have to find angle C. I should not use the 31.1 because that's not the true length. This is the true length, the square root of 969. So if I want to write it as square root of 969, then I could use it. But what if I calculated it wrong? If I calculate this wrong, or if I rounded, then every answer, every angle that I base off using this side may also be wrong or might be rounded wrong. So as I find stuff, I should only use what was given in the picture. So as I find angle C, this is the adjacent and this is the hypotenuse. Adjacent and hypotenuse are cosine. Cosine of angle C is 20 over 37, which means the measure of angle C is cosine can be found by doing the inverse of that ratio. So cosine inverse of 20 over 37 is 57 degrees. There's the measure of angle C. As I go to find the measure of angle A, the 20 is now the opposite. The 37 is still the hypotenuse. Opposite and hypotenuse is sine. So the sine of angle A is 20 over 37. To find the measure of angle A, since I have the ratio, I just need to do the inverse. So sine inverse of 20 37ths, sine inverse of 20 37ths is 32.7, so 33 degrees. When I'm done, I should make sure that these two angles add up to 90, and they do, because the 90 plus the 90 will add to 180. I do not want to use triangle sum to find this one after I find the 57, because if I plugged it in my calculator wrong, or if I rounded wrong, then I would get both answers wrong. Whereas if I calculate them separately, then I can verify they add to 90, and I know that I did it right. For letter B, this time we were given two of the angles in a triangle, so we can use the triangle sum theorem. 180 minus 90 is 90, and 90 minus 23 is 67 degrees for angle T. However, I don't want to use that, even though I'm really super confident in that answer. I don't want to use that to calculate my other sides. I want to use the information that was given. So as I go to find side R, I'm going to use the 23 degrees and the 35. With respect to the 23 degrees, this is the opposite and this is the adjacent. So the tangent of 23 degrees is equal to R over 35. When I cross multiply, I get that 35 times the tangent of 23 degrees will equal my value for r. 35 times tangent of 23 degrees is 14.856, rounded to the nearest, oh, if it was nearest hundredth, it would be 14.86. Well, rounded to the nearest tenth would be 14.9. And that's for side ST. Lastly, I'll look at measure of angle R, or not measure angle R, side RT. With respect to the 23 degrees, this is the hypotenuse. With respect to the 23 degrees, this is the adjacent. Again, I'm not using any of the values I just found. I'm using what was given in the original problem. So adjacent and hypotenuse is cosine. Cosine of 23 degrees is adjacent over hypotenuse. As I cross multiply, I get s times cosine of 23 degrees equals 35. So s will be 35 divided by cosine of 23 degrees. So I do 35 divided by cosine of 23 degrees in my calculator. And I get 30.02. So if it was rounded to the nearest hundredth, it would be 0.02. But it's rounded to the nearest tenth, it'll just be 38, or 38.0, which is still 38. And that's the length of RT. So we were given a side. We have found the other two sides. We were given two angles. We have found the other angle. We have found all sides and all angles in the triangle. This concludes clip 2 of the video notes for lesson 4.1. The learning target for this lesson, using angles of elevation and depression to find distances, and reviewing how to solve for all sides and angles using SOH-CAH-TOA and inverse trig ratios. Have a great day.